I kind of already talked about this, but the one of the main, working in Trinity College makes motivation for this easy because Dublin is one of the worst cities in the world for congestion. As you see, only Bogota and Rome are worse. I don't know what's your regional competition here with Rome. Are you glad that traffic is bad there or not? But at least Rome, and in particular Bogota, have an excuse. Bogota has 8 million people, Dublin has 1. We really have no excuse to be so inefficient with traffic as we are. And it's not just traffic, it's how we use renewable energy, how we use sensors, and so on. The application areas that I'll be focusing on in the talk are 2 smart mobility ones: urban traffic control, where I'm talking about RL agents being traffic lights; shared mobility, where I'm talking about RL agents being vehicles; residential demand response, that is smart grid application area where devices themselves learn when to operate based on price of energy, availability of renewable energy, or so on. So RL agent in this scenario is electrical device. And wireless networks, 2 types of wireless networks. We're starting to see drones being used more and more to provide various services to cities, from delivery, emergency deliveries, such as, or transplant organ delivery, or just actual food deliveries. There's a company that delivers you coffee by a drone in Dublin, only in kind of very remote areas. I do not have luxury of getting my coffee delivered in the urban area, but we're moving that way. And the other one is scheduling sensors in large IoT networks in such a way that we get information from them as often as we need it to, so that they do their purpose, but while maximizing their lifetime if they're energy constrained, whether because they're battery operated and replacing battery with require access to remote areas, or better because they rely on energy harvesting. So it depends on how much energy they can gather from sun in a particular day. And in Ireland, trust me, that's not much. The underlying characteristics of all of these areas that I talked about, and this is what makes them, fun for me to tackle, and what makes them suitable, in my opinion, for reinforcement learning, is that they are very large scale. So if you look at the map of the city there on the left, that's a Dublin road network. Each of those intersections in the graph is an intersection. It's an agent that needs to control the traffic and collaborate with other agents. All of those nodes in that large scale graph have their own goals. Sometimes they have common goals. So the traffic lights obviously have to, work together to optimize the traffic in the city. But some of those goals can differ. So you always want to prioritize ambulances, of course. That's there's no negotiation there. But you also want to prioritize public transport. That's one of the policies that city deploys, to prioritize public transport. If you have a road which has public transport, but not many other cars, but another road that has a bunch of private vehicles, if you just blindly always prioritize buses, the private vehicles will never get there. So these conflicts and trade-offs are a bit more subtle in certain situations. And another tricky / interesting characteristic is that operating environments are changing constantly, and that's one of the big things that RL was struggling, and is still struggling to deal with. That the things change. RL learns something, and then what it learned changes. The same way, if you learn how to do something, and then everything from under you changes suddenly. As an example there of illustration, that I have a graph. So the lower graph shows 1 month of wind generated energy in Ireland. And you can see that, some of the days that's nearly down to 0, whether there was a fault or whether there was not wind. While on the other days, we're reaching days where we're mostly powered by renewable energy. I was actually reading there the other day that California recently reached its highest, 99.87% of their daily use was from renewable energy. So a lot of it, we're moving towards renewable energy, but it's highly unpredictable. It depends, it depends on the weather. In Ireland, that's wind. In other countries, it's cloud coverage if you're relying on solar power. We can predict these to some extent, and the upper graph is a zoom in of 1 day of predicted energy from wind versus actual energy of wind. And you would think that we can predict that reasonably accurately. You look at the weather, weather forecasters are reasonably good at their jobs at this point. We know what's the weather going to be like. But even in that case, if you look at the two lines, the predicted versus actual can sometimes differ by even up to 1/3. So, how do you adjust the system when you have 1/3 less energy in the country than you expected to have? How do you reschedule all the devices, factories, data centers? That's a big one in Ireland. We have a lot of data centers that are using up all the energy, and we have, level of service agreements with them that we have to provide. So this is where reinforcement learning comes in. The first, to kind of motivate that I think these problems are too complex for them to be solved the way they are solved mostly now. So that's a picture from a traffic control center where, these three poor guys are trying to make sense out of information they're getting from, 50, 60 cameras and fix the mayhem that's happening in the city. There is too much going on. They have massive experience, and we don't want to lose that. I think one of the biggest challenges is how to make humans and RL work together. But there are some things that obviously RL's trial and error way of resolving them will become very, very beneficial. So obviously the way to learn it, in my opinion, is reinforcement learning. How familiar is everyone with RL? How many people have implemented an RL agent? I don't know what your undergrad, postgrad courses are covering. Okay. And how many are aware of RL as the concept and roughly what it can do? Okay, this is great. So asking this question kind of over the years, I'm glad to see more and more hands coming up, as obviously RL has had a big breakthrough. A couple of years after neural networks had a big breakthrough because we've expanded tabular RL with neural networks and big deep minds, Atari playing DQN, and then AlphaGo were the ones that put RL on the, on everyone's map. Most importantly, put it on the map of funding agencies. So people are very happy to actually give me grants to work on this these days, unlike in the early days. So there's a lot more work happening in RL now than it was, 10, 15 years ago. But basic idea of RL is agent is given some representation of the environment. What's relevant in the environment for it to learn. So if it's a traffic light, it's given, the road layout and how many cars does it have at each intersection, what's the vehicle type, possibly what's the occupancy, depending on what granularity we want to go. And it's given a couple of actions. Those are the combinations of traffic light settings. And through trial and error, it tries all of the possible combinations of things and sees what works and what doesn't work. Basically, this is what we call AI. It doesn't sound particularly intelligence, but the intelligence comes from doing this many times fast and intelligently combining the information we get. So we do an action and we get a so-called reward from the environment, which is just observing whether what we did was good or bad for the goal we're trying to achieve. And this is great. This works. It's guaranteed to converge to an optimal solution on a single agent with a single goal in a static environment. And all of the environments that I talked about now are none of these things. So what happens once we have, as in the situations that I talked about, we have multiple agents with conflicting goals operating in dynamic environments, all of this happening together, and all of this needing to happen quickly. So it's not just that we want to optimize the final performance, we want not to make too much of a mess while learning either. So we want to minimize so-called regret, which is the better performance we get while we're learning what to do. So to address bits and pieces of this problem, over the years originally with my PhD supervisor and postdoc supervisor, and now with a bunch of PhD students and postdocs and collaborators and so on, I've been working on, on fixing aspects of this, and those are the algorithms that I'll talk about. We've developed algorithms for RL that address the problem of simultaneously having multi-agent, multi-objective problems, addressing RL for non-stationary environments by incorporating that prediction and then classification towards the closest previous behavior we've seen to make this work in non-stationary environment. A lot of work on speeding up the learning time, and particularly in multi-agent systems, there's a lot agents can learn from each other through various multi-agent collaboration ways, but also through transfer learning, which is the work we're focusing on now. Obviously, how fast you learn depends on how optimal your representation of environment is. So we've been doing work on RL learning its own state representation rather than it being predefined by humans. Some of the work on combining this with programming languages to make this more accessible to people who don't know and don't want to know RL because it's not their job to know RL. So to make this easier for adoption in real computer systems. And recently, a big shift, not just in RL, but everywhere in AI towards explainability, given we have a draft at the moment, but we will have in a couple of years an EU legislation on various aspects of AI, one of them being that if AI makes a decision about you, whether that's your loan, whether it's a college admission job or whatever, you are entitled to be provided with an explanation. Why did AI make that decision? As well as provided with an option for recourse, which says, okay, if your application differed here, or if this was different, you would have gotten a different decision. And we don't know any of this about RL and in general about AI. For so many years, it works, don't touch it, don't go near it. Just, you tweaked it to the point where hyperparameters suit, it works brilliant. So there's a big push to work on that. As you see, there's 5 or 6 things there that I'll have to go through reasonably quickly. But the idea here is, to give you a flavor of the space of the current work that's happening there. And this is just a small subset of the work that's happening in RL. When I say multi-agent, multi-objective RL, it's one off. There is so much work on multi-agent RL, less on multi-objective RL. But some of those, so when we started developing this, there was nothing that combined the two. And this is still being used in various application areas. But there's each of these sections obviously will present, work that I know the best, which is mine. But if you're interested deeper in that area, go to state of the art of any of those papers, and you'll find a lot more to get you started. So for the multi-agent, multi-objective or multi-goal systems, a lot of the work focuses on homogeneous agents cooperating. So, you and I have the same goals and we want to achieve something and we have the same capabilities and we cooperate to achieve it. So look at it as a kind of group assignment. What happens if agents have different goals? There might be, some of the goals might be the same, some of the goals might not. So each agent wants to meet its own goals, but it also, for the good of the overall system, it wants to, if possible, help other agents, but at the very least not interfere with performance of other agents. So the technique we've developed for that, it's based on a single agent technique that balances multiple objectives on a single agent, but it works by adding this collaboration coefficient and works as nicely on multi-agent space, where I, as an agent, have a bunch of those, simple RL processes that I showed there on the slide, learning for each of those how to meet one of my goals. So how to optimize traffic, how to prioritize ambulances, how to prioritize public transport. Other agents have their own goals, and they also learn how to meet theirs. What happens is when we operate in the shared environment, and traffic is a good example of a shared environment, no matter what I do as a junction, if junction downstream from me is congested, I will just have the backlog and the cars at my queue will not move because the other junction is not performing. So that's a very strong case for collaboration. So what we started adding to agents, apart from learning these local things, is learning how what I do affects other agents. And obviously that's not scalable in a large system. So you have to limit it to your neighborhood where, for example, in a junction scenario, I learn how my actions affect one-hop junctions from me. Then the one-hop junctions learn one hop down and so on. And that seems to work. It's scalable because it's localized to a neighborhood, but it works. So at each point, I learn what I need to do to meet my goals. I also learn kind of what would I ideally do to help other agents meet their goals. I don't need to know what their goals are. All I know is when I do something, the other agent tells me, yeah, don't do that, or yeah, that was great. Other agent doesn't care, so there's some privacy maintained. Other agent doesn't care why I did it. It just cares whether it was good or bad for itself and passes that information. So every time I want to make a decision, I can decide, do I do what's best for me? Do I do what's best for any one of my neighbors? Do I do what's best for overall community? So do I sum these pieces of information that I got from other agents? And also I can decide how to weigh my preferences versus other agent preferences. And this is where we introduced this collaboration coefficient. So if we leave this at 1, it means I take other agents' preference into account as much as my own. If I set that at 0, means I don't care what other agents think. It turns out that the correct number, and where correct obviously differs per application area and per situation, is somewhere in between. And of course, it's hard to come up with a number. So we've added an extra layer of, again, learning on top of RL, where agents themselves learn how much to collaborate for the good of the system. And you notice this varying anywhere from, in some situations, for some important junctions, 0 might be the right coefficient because this junction has such massive impact on traffic that it doesn't need to collaborate with the others. Just by doing well itself, the knock-on effect on the others happens. While in some smaller junctions, they do need to sometimes yield to more important junctions fully and do whatever actions they say it. And this has turned out surprisingly useful in a number of areas. In some of the early work, we applied that in urban traffic control. Then we applied similar technique to that renewable energy use. Recently, we've had a paper on combining this with software adaptations in self-adaptive systems, where you have multiple adaptations wanting to modify the program execution, and you need to decide which one takes bigger priority or which one will satisfy the most objectives. Also recent work on, it's also in mobility, but a slightly different application areas on variable speed limits on highways, having different parts of highway partitioned to figure out what's the optimal speed limit to set at that region, but also collaborating with neighboring regions to make that process smooth rather than jumpy. So that's it for the multi-objective stuff. For non-stationarity, a couple of things that come into play here. So if something changes in the environment that RL agent is doing something, that could be just a function of environment, so it just might be less windy, and that's why we don't have enough energy. Or it could be something another agent is doing. So there might not be enough energy because another agent has turned on all of its devices and it's using it up. A lot of the work focuses on collaborating with other agents, not to do that, or in synchronizing, jointly deciding actions with other agents to make sure that, to minimize that stationarity. If the agents are not collaborative, it's trying to predict what would non-collaborative agents do in order to learn its own behavior. The work we do is focusing on, we don't care what the cause of this is, but whether we can predict the patterns in which it would change and just learn how to react to it. So it's kind of all on us, what happens in the environment. We don't care where it comes from. It's us that have to deal with it. And I like this work because it combines so many aspects of AI. It's a very good use case for kind of showcasing different types of learning. The first thing we have to do is, and we use this in the energy scenario where you have devices that need to operate, that need to use energy. So we're talking electric vehicles need charging, or air conditioning needs turning on, washing machine needs running. Some of these things doesn't matter really when exactly does it happen, as long as they happen within the allocated window. So, you want your car charged in the morning, or you want your clothes dried before you go to work. You first have to continuously monitor environment, so both energy use environment and renewable energy generation environment, in order to be able to feed that prediction to agents to make the decisions. And when those predictions are fully accurate, you can use any RL to make decisions based on that. But it's when they're not, when there's an anomaly, you need to, first you need to figure out, this is time series data coming in. You need to figure out if this is just an anomaly, a glitch, an outlier, or is this some new pattern that's changing? And if it is some new pattern that's changing, you need to, in order to know best what to do, ideally, first time you see it, you won't know what to do, but you'll learn and then remember it for next time. When you detect it next time, when you see the change next time, you need to classify it into one of these previously seen behaviors, or at least find the closest one to it, or at least figure out it's so different from anything you've seen before that using transfer learning on top of something would just slow you down even more, because you have to unlearn things in order to learn new ones. So it's classifying the change you've seen and then learning how to do that. We've applied this in that smart grid scenario, and it takes us about, this is, the application of trying to figure out how to minimize the loss while learning. If there's a change in either energy usage or energy generation, it takes us about 2 hours to be, confident that it's an actual structured change rather than an outlier, and to classify it in which of these previously seen conditions it falls under. What I mean by previously seen conditions, there are different patterns in which people use energy. The way you use your energy on Monday morning is different from the way people use energy on Saturdays. There's clear, of course, this has all been thrown off with working from home, but energy use used to be, pretty clear. The morning spike, then not much during the day, afternoon spike, then not much during the downtime. So it's learning those patterns and positioning them in one of those. Once we know which of these categories does the new behavior belong to, we could pick up what we've learned and it works straight off, and it'd be amazing if it did. But a lot of the times it still needs tweaking and adjusting to the new environment, but we have some basis to start with. And what we do then is use transfer learning techniques to to bootstrap the new learning processes. Traditionally, transfer learning has been developed as a way to learn from one task and transfer it to another. So, as a child, you learn how to climb the stairs, and from that, you kind of figure out how to climb the things on the slide to get up on the top of the slide. Transfers between similar tasks, but it still needs some of the adjusting. The work that we're trying to do and the work that there is obviously some other work happening as well is learning how to share this knowledge online between multiple agents. Because, again, if you look at a traffic light example, traffic lights might have different layouts, which are different state representations. They might have different action sets, which is the different combinations of traffic lights, which again is based on their underlying structures, how many lanes and approaches does it have. But ultimately, they're all learning the same thing. They're all learning to make the traffic go smoothly. So there's a lot of knowledge that can be reused. The tricky part is identifying what can be reused, who it should be shared with, so which agents are similar enough to you that your knowledge can benefit them. How often should you share it? And who becomes at each interaction, who's the teacher, who's the student. So if you picture yourself studying for the exam, if you just met a random stranger to study for the exam with them, there might not be nothing to share. If they're learning about history and you're learning Python programming, there might not be any need for transfer learning there. You need to identify that situation. Or if you're figuring out, even if you get to the point of figuring out you're learning for the same exam, which one of you knew better? If you're disagreeing on something, who's right? At each step, there's a lot to be gained from, having a study partner or multiple agent, but there's also a lot of decisions to be made how to identify these things. And of course, all of these things differ by situation. That was an example of you studying for one exam. What if you're studying for another exam and there's another person? You have to start all of that from scratch. So the things such as how to select which knowledge to transfer, how to select which agent to transfer it from, how to select which agent to transfer it to, and then how much does the receiving agent trust that input that it got are all decisions that have no answers to, unfortunately, because it's another thing that we're noticing obviously differs per situation, and another thing that we're currently trying to move online. So, from the kind of doing this in a static way, the answer to it obviously is it depends. So what we're doing now, and in the kind of large scale scenario where we did with 200 agents, it differs per every agent. Benefits are more trade-offy than obvious. There's no simple line here. The final line there is the L is transfer learning. The final line there is the approach. You gain some in that you have lower waiting time, but you're serving less requests. This is in a ride-sharing scenario. So this is the work we're doing now on trying to automate these decisions, for each agent or each group of agents to figure this out themselves. Again, as another kind of meta reinforcement learning process on top of RL that happens there. Another thing that I started working on this because I was just so annoyed over the years on, on how to design an RL agent. And if you've ever, if you've been learning RL in any of your courses, or if you wanted to develop your first RL agent, first of all, what information is relevant? What do you feed to an agent? What features do you give it to base the decisions on? If you're using neural networks, your decision is just the features. If you're using tabular, your decision is what granularity to give it to. So, take this example that I have on the slide. How do you represent these two pictures? Is busy not busy enough? Is, what would that be enough for agent to make all the decision it needs to make? or it needs an information, there's 5 cars in first picture and there's 20 cars in another picture. You would think that, it's always safer to give it more information and it doesn't have to use it if it doesn't need it. But that ridiculously lengthens your training time. Whether you have 2 states, busy, not busy, or whether you have a state where, you have 1 car, 2 cars, 3 cars, 4 cars. It takes a lot longer to train. Some of that has been removed by, you're just having a number of inputs into your neural network. But you're just kind of really shifting that problem deeper into the network because, your inputs are fixed. Those are the features that are relevant. Your outputs are fixed. Those are the actions that your agent can learn to do. And it decides which one is the best based on these inputs. But how complex is the inside of that network? How many layers do you have? And how many neurons in each do you have? Matters because the more fine-grained behaviors you need based on the input, the more complex that inside part needs to be. If you just need to make a simple decision based on busy, not busy, then you need a single layer. You don't need a deep neural network. It'll be, if it's busy, set the green. If it's not busy, set the red. But it's very rarely simple as that. And, all of this is trial and error. I've been supervising student projects in RL for many years now. And I always feel so, what do we know about RL? Every time when a student asks me, so what should I put in the state space? And I go, well, try it and see, So we're trying to eliminate some of this by having agents pick up things that it observes from environment and build this kind of neural network on the fly. So we're not committing to the full neural network with a structure which is there beforehand. We're not giving it a tabular state space, which says these are your fixed states. We're getting a piece of information from the environment, doing an action. If that action ends up getting positive feedback, we use this in, what's illustrated here is a 2D space, but you can have it along any number of dimensions based on how many dimensions your input has, how many features you're inputting. Covering the regions of the state space with that action. So, if actions happen to be a good action in this particular state, unless there's a closer region covered by another action somewhere during the execution, area around me belongs to that action. So instead of having this grid-like representation at the bottom, we end up with a lot less of these individual points, which kind of act like state space input. We're using growing neural gas to expand and shrink the number of nodes that we have. So if a node hasn't been used in a while, if an action hasn't been executed and proven to be good, we drop it. If it has been shown to be, better or worse than it was, we move it slightly in that n-dimensional space towards where it's getting better feedback. If we end up noticing a lot of actions with a small change in the input, noticing scale in actions, difference in actions, we end up adding nodes in between. So it kind of grows. It's like a neural network behavior. So it has the ability to generalize, but you grow it on the fly, deciding how many of these nodes you need, as opposed to fixing the structure before that. And when this is the output of that on the standard mountain car behavior, the standard car benchmark. Original mountain car tabular representation has 100 states, which is 10 for speed, 10 for position. This is the one on the left. When we use our multi-layered growing neural gas on that, we end up with whatever number of those scatter dots around there is, reducing the state space size, which is good because we then learn quicker, but we get exact same performance with this number number of states. Again, applying that to larger scenario, which is what inspired all this, those 200 agents from ride sharing scenario that we've seen before. The graph on the right shows original state space. So the tabular representation would have had 125 states. Each agent out of those 200 figured out how many of those states are relevant for it by building its own G&G representation of it. So some of them, so no agent had more than 30 states, which means we were absolutely overkilling it with our original 125. Most of them you see converge there to around between 20 and 25 states. And it's like, this is what you need to learn. So agents were identifying in the environment themselves what's relevant there. I will quickly go through, I'm keeping an eye on time, so I will quickly go through this one as it's kind of side point because it's going more into software engineering. But to make RL work, you need to know RL. You have the constructs of RL that are hanging around in your code. You have states, you have actions, you have replay buffer, you have various parameters and so on. Once you learn that behavior, can we just make those behaviors clean for the reuse in the rest of the system? So, one junction learns what to do. We use reinforcement learning options, which is learning the sequences of actions. We learn the sequences that agent did, package those sequences in context-oriented programming constructs called adaptations. If you think of it in terms of object-oriented, that is your method. In context-oriented programming, it's slightly different, that it is triggered by the detection of a different context, but the unit is same as method. You package whatever RL learned and then make it modular for reuse for the rest of the system. You still have RL relearning things. Every so often, those adaptations get repackaged, new ones get sent, but it provides modularity and kind of ease of use for the rest of the code rather than entangling RL in with everything. Use that in a very simple example of just car learning how to overtake, because when you're overtaking, you go left or right. I always mix up who drives on which side of the road. You go to whichever side you overtake on, speed up, overtake the car, merge back in. Those are all individual actions in RL: speed up, slow down, steer left, steer right. You package those in an action overtake, and when a car needs to overtake, you just do action overtake, and it executes that sequence. My favorite piece of work at the moment is explainable RL, and it's not very far, and it's not just our work that's not very far. There's very little on explainable RL, so I'm looking forward to what this area will bring over the next few years. One of the small aspects of that we're addressing is trying to untangle causality from correlation in RL. And I know, good luck trying to untangle that even with humans, never mind with RL. But you would have, so one of the main things of explainability is, both in supervised learning and in RL, is identifying what feature or what values of certain environment set of conditions were crucial for making the decision. So again, to use the loan scenario or admissions or whatever, you weren't admitted to your postgrad because you failed, your intro to programming. Identifying what was it that caused that action of RL. But often, because, RL just does blind trial and error, a lot of these things end up, it's impossible to tangle what was correlated with you not being admitted to postgrad versus what caused you not being admitted to postgrad. Maybe you weren't admitted to postgrad because it was sunny that day, or you weren't admitted to postgrad because you happened to be traveling at that point. RL doesn't know what was caused versus what was just correlated with it. In a lot of the cases, that doesn't matter. As long as it works, it doesn't matter what was the what was the cause. It is when we try to A, explain it, or B, when we try to move it through transfer learning, or if there's a change in environment, when we try to reuse that behavior in another similar environment where there might not be correlation. So the underlying causal structures are the same, but the same correlations might not hold. If agents was relying on correlation to infer something rather than on causation, that breaks. So that's where that work is relevant. And we've no intelligent way to do this at the moment. The best way, and this is more than the community is doing at the moment, is to identify some critical states in which it matters whether a certain part of the state was cause or correlation, and create these alternative worlds in which we remove parts of the state space that agents was basing decision on and see how agents perform in that environment. And it will perform well in cases where it learned correct causes. It will perform worse in cases where it was just relying on correlations. That is it for the big 5 topics that I talked about. In terms of new application areas that we're starting to apply this in that didn't yet bring any new developments, but this is kind of what will shape at least mine and my PhD students' research for the next while as well. Is applications of this in communication networks. And one thing I'm noticing, and it's a completely new application area to me, I had to learn a lot about it in the past few years, but the scale of decisions needs to happen way, way quicker than in the environments that I've been previously working with, which we're starting to struggle with, obviously, because RL takes a lot of trial and error to learn. So some of the work that both this and next slides are off-the-shelf RL algorithms applied in this area to see how they work, because we're at the stage of identifying what's missing. So the work on providing good connectivity to UAVs while they're doing what they're doing, deliveries or whatnot, but also in case of needing higher network coverage after certain events or outages, positioning UAVs so they act as base stations for ground users to connect to, and how optimally to position and have those UAVs move. If you see on the graph, that's them coordinating and figuring out where to position themselves based on how the underlying mobile users move. So if you're leaving a concert, or if there's a evacuation or whatever, if there's increased number of users there. In terms of IoT network, the big thing is energy constrained devices. RL takes a lot of data, which takes a lot of training, which takes a lot of energy. We cannot train this on an energy constrained sensor, but we still want energy constrained sensor to use RL to make intelligent decisions. So what we're trying to do is come up with techniques to train RL agents on a more powerful device than a thing kind of clouded somewhere, figuring out what's the right frequency with which to transfer the weights to the constrained device to still maintain accuracy, and the correct behavior, but obviously without wasting, we're wasting sensors energy on running RL, which is designed to save sensors energy. Doesn't make sense unless we get those trade-offs right. So to summarize, the things that we can do is, multi-agent, multi-objective collaboration. We can generate some state spaces from the observations rather than predefine them. We can share knowledge using transfer learning. We can adapt to changes in the environment. We still have a lot to do in that space. Learning online and sharing knowledge online, that was my big I don't know there, because we still need to learn how to learn those things. So automating that is one of the big things. Giving any performance guarantees about this, that is another big one. All of this, if it works, it works. Don't touch it. If it doesn't work, not much I can do. So, and since RL and AI in general is being, more pervasive in everyday software systems, there's a lot of work we're doing on testing RL-based software systems, and how do you test the behavior when you don't even know what the correct behavior is? Because if you did, you wouldn't need RL to learn. Explanations, that's another big one but we're still in the infancy with. And also combining all of this with how humans learn. So remember those guys in the traffic center I showed at the start, they know a lot about this, so they could provide helpful input to agents learning. But how do we make agents and humans interact in a meaningful way to teach agents the good things? So if you just look at a human as another agent in transfer learning scenario, what does this human know? Does it know better than me? When do I need to learn from it? And also, how do I communicate with it? If I as an agent can't explain my behavior, how can I communicate with a human? And that is all I had. Before we move on to the questions, just also to say that, since you saw there's a lot of work to be done, and I'm always looking for people to help me do it. So if anyone wants to do a PhD in any of this, or just finishing PhD and wants to do a postdoc, do drop me a line. RL seems to be a good space to be at the moment. So yeah, funding agencies are giving us money, so make the most of it if you're interested in proceeding in this research direction. Thank you.
Thank you. So turn this on.
Do you want this one? Oh, no, you can't, because then you'll have to answer my questions. Use this one.
Try the other one. This works?
Yep.
Okay. Okay, we got time for a few questions. If people who's following remotely want to ask a question, please raise your hand in Teams. I should be able to see. If there are questions from the room, okay. Closest first.
Whoever's closer.
Very good talk, first of all, but I have a question about distributed W learning. How do you handle the neighborhood? Is changed over time or is fixed?
In the work that we did, it was static, and that's if you were doing it where neighbors changed, the change would have to be part of the environment, because what you learned about one neighbor is in no way relevant to another neighbor, or it might be. So it's a kind of very tricky mix of that collaboration in non-stationary environment with transfer learning, because you might be able to transfer something from what you learned about your neighbors to other neighbors, or might not. So yeah, the answer is no idea, but this is just direction in which you could start solving that problem.
Okay, and I have another question. And what about partial observability? In the problem you exposed, I assume that agent does not have all the information about the environment. Suppose you have a camera and use all the image, right? Or
in which work? Explainability
about UAV, I think for what kind of use case you use UAV?
With the traffic
yes.
scenario, yeah. So we avoid using camera images for any of this, purely because it's about the longest training time you can have. Because it's only if you don't know anything about environment or anything what's relevant in that picture for traffic, you would use the image, because agent spends, initial large chunk of its training time to identify what's even relevant and then to quantify it. So, agent would first think, okay, is that bird relevant? Is the color of the car relevant? So we, for that work and for anywhere we can, we try to give it specific features rather than the images. In this work, it was fed as an integer, but the agent was deciding whether to represent it as a discrete number, 1, 2, 3, 4, 5, to represent it as low traffic or not low traffic, or to put it in a bracket between 0, 5, 5, 10, and so on. So it was fed, whatever is fed is determined by what sensor we have. But it's the how agents chooses to represent it that was learned.
Okay, thank you.
Thank you.
Okay, let's try to take a question from
There was another one, yeah.
I'm switching one from the
Okay.
room.
Oh, okay. We're being fair.
I want to
Okay.
be as fair as
Thank
possible.
you. Yes.
So, Andreas, if you should be able to open your mic if you want, ask a question.
Thank you very much. Can you hear me?
Yes.
Yeah, we can.
Thank you very much. Great talk, Ivana. Really brilliant. I very much like it. We also work with reinforcement learning for quite some time. And you're fully right that it's a rather appealing technique because you don't have to explicitly code adaptation rules like in the past, and you can react to environment changes. The thing is, of course, you have to specify the reward function still as a human, right? This is not kind of given by the algorithm or the agent itself. Can you share a little bit your experience in the reward function engineering, how difficult or complicated it may be, maybe some pitfalls, and even more interestingly, maybe leading over also to the explainability discussion, how can you debug the reward function in the end? Because this will be the prime target the learning agent will try to optimize, right?
Yes, that's another huge area that unfortunately I haven't done any work on because it's even trickier than deciding on the state space. And it's again with explainability, as you mentioned, it's becoming even a bigger deal now because so traditionally we used to define AI as learning how to autonomously meet its own goals. The new kind of definition that we're mostly accepting now in the community is AI agents that autonomously learn how to meet human goals, because we're figuring out that humans are not so good in translating their goals to agent goals, and agents end up doing what we told them to do, which then turns out isn't what we imagined to do. So there is work to be done on exactly in that field of human agent interaction and collaboration, how to refine these, where, the first go at, at any, I don't know, the example I use, it's a bit dark, but, it classifies it really nice. It explains it really nicely is, you give an agent a goal to eliminate cancer. Agent goes and kills everyone who develops cancer, problem solved. But that's not what humans wanted. We just didn't express it as fine-grained as we thought we are. So it's, again, another question that I don't know. And that what I know about RL was that hour. What I don't know about RL is the rest of my life. So I think we're all in the same boat. But that's what makes it, that's what makes it interesting.
Yeah, and it's already good to know what is the challenge and the limitations maybe you have to face and have to be careful about, right? I mean, this is where things start. And not really use it naively, just out of the box and hope for the best. I think your car crash at the beginning showed this very nicely.
Yeah.
Thank you very much.
Thank you. And if anyone was interested in more kind of lightweight reading on this topic, I finally got around to reading the alignment problem book on the flight over. And it does talk a lot about these things, about disalignment between human goals and what AI ends up having. And, even if we were to if we notice AI isn't doing what we told it to, but without explainability, we don't know even, what the confusion is. We don't know how to help it. So it brings up a lot of these issues on explainability, but in the context of RL as well.
Okay.
Excellent. Thank you again.
Thank you.
There was one question from the room.
Yeah, Ivana, thanks for your talk. I have a question about the collaboration coefficient factor. That's a coefficient that each agent learns independently from other, yes. And it's private to each agent.
Yeah.
And I'm curious about how to learn that. In the sense, do they learn this in parallel while they are doing reinforcement learning? First thing, and second thing is, I know nothing about this, but the suspicion I have, it may depend on the policy you are learning. So it's like a vicious feedback cycle. You may.
Yes, exactly. And again, as my answer to everything in RL, you just have to try it and see. But what we found, yes, it's exactly that. It not just depends on agent, but it also depends on what you're trying to learn, because it just might happen that your neighbors at that particular point are just doing exact same thing that you're doing, and that there's no competition at all, and it all works perfectly for that particular policy if everyone is doing that same thing. If we change the goal all of that becomes obsolete because, you know, if there might be different actions that neighbors need to do in order to achieve the same goal. So you have to start from scratch. So yes, the only way we found that it works is to learn it in parallel with learning the original policies. Welcome.
Okay, Kushal, if you want, you can open your mic and ask a question.
Thank you. I hope you can hear me fine.
And thank you. Yeah.
Thanks for the presentation. I have a question on the COP RL slide. You had mentioned that you need to manually choose the actions that the agents can perform at design time. So is this needed in all of the scenarios, or was that specific to the implementation aspects you were talking about?
In all of them. So the reason that was brought up in COP is because the sequences and the kind of groups in which those individual actions come are predefined. In RL, you still have to predefine what are possible actions, but you don't predefine in which sequences they're executed. Agent learns what to execute when and in which sequence. So it's that benefit of RL that we've been trying to combine with COP to avoid that having to be manual sequence.
Got it. Thanks.
Thank you.
Okay, let me check if there is another question from the room. I see. Okay.
Hi. So the example you described in which agents had policies concerning the neighborhood. What about the size of the neighborhood you consider in your examples? And in the case this is dynamic, as Gianluca was mentioning before, what about learning which part of the neighborhood I have to care about?
Yeah, so the size was reasonably small. In traffic scenario, it's whatever your neighboring junctions are. So that ranges from 2 upstream and downstream to 4 or 5 max. In energy scenario, the natural unit would be, so when we were working with households, the natural unit in terms of how energy infrastructure is organized would have been about 90 households. But we found that to be way too messy because you didn't know whose policies you're meeting at that point. So we limited it to 9. And how do you identify them? Well, you don't manually identify them. You just kind of post-observe which junctions learned that it's best not to collaborate with anyone and that that's the best performance for the system. And we kind of decided those would be the most influential ones because, if other neighbors need to collaborate with me, but I don't need to collaborate with anyone, means I'm very important, means I'm the head of university. So that's kind of the post-analysis we did. Again, if you know which junctions are important, we didn't do that work, but it makes sense to seed some of these values to, give them a kickstart.
Okay, we're time, but let's take the last question. Ilias, if you want, you can open your mic and ask.
Oh, thanks a lot. Can you hear me?
Yeah, we can hear you and we see you.
Great. Hi, Ivana. Thanks a lot for the talk. I was wondering. Yes, I was here. I was there actually. I was wondering, on the your work you did on the closer to software engineering, right? Because we have been also a couple of students looking into some RL recently. My impression is that is what you said actually at the end, that it's very hard to generalize, right? So you get to a domain and you get to a particular setting that you know very well, and then you calibrate your models. You select first and then you calibrate. So I was thinking, if we are to go and use RL, let's say in a software system, where you have the chance of stopping the system, like in a traffic system, you don't have that chance. That's a live system, right? That just happens to be like that. But in a software system, if we are to engineer software systems that use RL, we want to probably have some guidelines, right? So what are your thoughts on this? What are the big challenges in moving? Is it the testing that you mentioned? Is it the tooling? Is it the lack of expertise? I was just wondering.
All of the above. So the work, and a bit of a semi-private answer is that Nicholas is your man for COP work, because that's the joint work we're working on. But we're started to exploring a lot of this work together with the software engineering community, because I don't know much about that. So I am working with a collaborator that Elias happens to know, Nicholas Cardozo, who is working on software engineering stuff. And yes, anything from, so there is testing, there is how do you incorporate this in a modular way, Nicholas has been doing some work separately on identifying different anti-patterns that come up when you work with RL as opposed to with other stuff, different code smells. It's once you throw in something that behaves and is structured so differently from non-AI software systems, because the focus is now on data rather than the code, everything needs to change. So yeah, the answer is all of the above, and we've been just dabbling into that work a bit, but software engineering communities are a lot more heavily involved with this now. So there's a lot of SE for AI and AI for SE and ML for SE and SE for ML and so on. So there's a lot of more work, I think, happening on that side, because more knowledge is required in software engineering side than on RL side. I break it, you guys fix it, please.
Well, I found most of your points very surprisingly close to what I'm interested in. So this is good. Also, the explainability aspect, for instance, is very relevant for software engineering. Thank you. Yeah.
Thank you.
Okay, I think we are 12 minutes past or ending or expected ending. So I'm closing the session now. We will get back in the afternoon at 1 with the next talk. That should be Alessandro, right? Okay, so guys, who's in person is, of course, free to go, have your lunch, and see you at 1 p.m.